Alright guys, in this video we're talking about 2.4 conditional probability. Pull out the marker. So first of all, let's take a look at the notation of the conditional probability. So the notation probability of A vertical line B is usually used to represent the conditional probability of A given that the event B has occurred. So when we're talking about a conditional probability, it is supposed to look like this. So this represents the probability of A given probability of B. Now, once we know the notation, once we know the notation of the conditional probability, let's take a look at the example here. And this example is coming from the textbook 2.24. So the problem says complex components are assembled in a plant that uses two different assembly lines, A and A prime. A and A prime. Line A uses older equipment than A prime, so it is somewhat slower and less reliable. Suppose on a given day, line A has assembled 8 components, of which 2 have been identified as defective. Of course, defective denoted by B, and 6 as non-defective. The non-defective denoted by B prime. Whereas A prime has produced 1 defective and 9 non-defective components. So this information is summarized in the company table. So we have the table on the left-hand side over here. And from this table, we can tell from line A, we have 2 defectives and 6 non-defective components. And from the line A prime, we get 1 defective and 9 non-defective components. So the question over here is asking, so what is the probability of line A component selected? So based on what we learned before, we know that if we want to find the probability, we got to apply the formula. The probability of A is equal to the possible outcomes in the event A divided by the total. Okay. Now, same thing here. If we want to find the probability of that line A component selected, first of all, let's say how many components are coming from the line A. So we got this row here for line A. So we get 8 of them in total. So this would be equal to, of course, n of A divided by n. And we know that there are 8 components coming from the line A. And the total would be, this is 8 and this is 10. So the total would be 18. So we get 8 divided by 18, and if we simplify it, we will have, this is equal to 4/9. That's the probability that line A component selected. So once this is clear, let's take a look at this question here. If we have known that the selected component is defective, then what is the probability of that? What is the probability that the component is selected from line A? So in this case, we'll say that we have already known the component is defective, which means if we put this question in a form of probability, we're looking for the probability of given that is defective, the defective denoted by B here. And we're looking for the probability that the component is selected by line A. So we're looking for the probability of A given B here. And then, same thing, if we want to find out this probability over here, let's take a look at how many components are defective in total, okay? So we're talking about this column over here. So we have 3 components are defective. So the bottom over here, and then how many of them are coming from the line A? We got 2. So the probability over here is 2/3. And then what I would do next is I will divide both top and bottom by 18. We get 2/18 on the top, and 3/18 on the bottom. So the fraction will keep equivalent to each other because we are dividing a same number by both top and bottom, right? Now let's take a look at what the top represent. We got 2/18. That's the probability, right? 18 is the total over here. It's 18. 18 is the total, right? And the 2 is coming from here. This is 2. And what does the 2 represent? The 2 represent A intersection B, A intersection B. So the top is the probability of A intersection B. And then let's take a look at the bottom. The bottom is the 3 over 18. Where's the 3 coming from? We have 2 plus 1 is equal to 3. So we got a 3 here, right? So 3 is number of defective components, which means this is the probability of B. Because this represents the number of B divided by the total. So that's the probability of B. And actually, we can also explain this question by drawing a Venn diagram. So if I draw a picture over here, the rectangle represents sample space, and we have A here, and we have B here. Okay. Now since we have already known B happens, which means we know this circle over here, right? We know this circle. And we want to find the probability that A given B. So we're looking for this part over here. So this intersection part is A intersection B, and then divided by B here, because B is given probability of B. And then once we know this, and we're going to get into the definition of conditional probability. So for any 2 events A and B with probability of B is positive, the conditional probability of A given B that has occurred is defined by probability of A given B is equal to the probability of A intersection B and divided by probability of B, which is exactly same as what we got over here. And that's pretty much the definition of a conditional probability. Now, once we know the definition of the conditional probability, let's take a look at this example coming from the textbook 2.25. So the problem says, suppose that of all individuals buying a certain digital camera, 60% include an optional memory card in their purchase, and 40% include an extra battery, and 30% include both a card and battery. Consider randomly selecting a buyer, and let A represents the memory card purchased, B represents the battery purchased, and of course, based on the number given in the problem, we have the probability of A as 0.6 and the probability of B is 0.4. And of course, the probability both purchased would be the probability of A intersection B, which is 0.3, given in the problem as well. So once we know those numbers in the problem, let's take a look at the question asking here. Given that the selected individual purchased an extra battery. So the extra battery is B, right? Given B. What is the probability that an optional card was also purchased? The optional card is denoted by A here. So if we translate this question into a form of probability, we are looking for the probability of A given B. Now, based on the formula or the definition of a conditional probability, we have that the probability of A given B is equal to the probability of A intersection B divided by probability of B. And then, what is the probability of A intersection B? The probability of A intersection B is 0.3. And the probability of B is 0.4. So we have, this is a 0.75. And this is not equal to the probability of A. So the probability of A and the probability of the conditional probability of A given B are completely different notations, right? Okay? Don't be confused. Probability of A is completely different from the probability of A given B. Now, once this is clear, let's take a look at number 2. given that selected individual purchased optional memory card. So the memory card was denoted by A. And what is the probability that an extra battery was purchased as well? So the extra battery represented by B. So if we translate number 2 into a form of probability, we're going to have this is the probability of B given A. So based on the formula we learned, this would be probability of B intersection A divided by probability of A. So of course, the probability of B intersection A is the same as the probability of A intersection B divided by probability of A. Then what is the probability of A intersection B? Based on the question, this is 0.3, and the probability of A is 0.6. So this is 0.5, which is not equal to probability of B, and of course it's not equal to the probability of A given B either. So once again, probability of B is completely different from the probability of B given A, and the probability of A given B is completely different from the probability of B given A as well. So don't be confused, okay? So basically, the key point of this kind of question is to know this formula over here, or to know the definition of the conditional probability. Okay, once this makes sense, let's take a look at one more example. This is coming from the book as well. The problem says a news magazine publishes 3 columns titled Art, Books, and Cinema. So A, B, and C. So reading habits of randomly selected reader with respect to these columns are, so we have the probability of A is 0.14, probability of B is 0.23, probability of C is 0.37, and so forth. And we want to find the probabilities below. First of all, let's take a look at the probability of A given B. So based on the formula we went over before, we know that probability of A given B is equal to the probability of A intersection B divided by the probability of B, right? So the probability of A intersection B is given here 0.08 divided by probability of B given here 0.23. And if you convert this to decimal places, that's approximately equal to 0.348. And then we want to find out the probability of A given B union C. So we just apply the formula directly. So we just consider this union as a whole thing. So that would be the probability of A intersection this whole thing B. Oh, let me rewrite it clear. Intersection B union C. So in this case, we consider this union as a whole thing, and then divided by the probability of B union C. Now, how can we find the probability of B union C? We know that the probability of B union C would be equal to, so based on what the formula we went over before, we know that the probability of B union C, the probability of B union C is equal to the probability of B plus the probability of C, and then minus the probability of B intersection C. Right? And we know the probability of B, we know the probability of C, and we know the probability of B intersection C from the table given here, so we can find the probability of B union C. But how can we find the probability of A intersection B union C? So what I will do here, I will draw a Venn diagram. So I will draw it over here. So of course, there's a sample space, and we're going to have 3 circles, A, B, and C. And then we know that the very center part, I may draw a little bit bigger to make it clear. I will I'll draw it over here. So we have A, B, and C. So this is A, this is B, this is C. Now let's take a look at this. Those three circles over here. So what does the very center part represent? The very center part represents, the very center part, this part over here, represents A intersection B intersection C is that. So the probability of the center part is 0.05. So we get a 0.05 here. And then let's take a look at this part over here. This part plus this center part would be A intersection B. That would be A intersection B. So A intersection B minus 0.05 will give us A intersect. That's right. That will give us this part, which is 0.03. Okay. The reason why we have 0.03 is because the A intersection, this part is the A intersection B, which is 0.08. And 0.08 minus the center 0.05 is 0.03. And then let's take a look at this part over here. This part over here represents A intersection C. A intersection C is 0.09. So 0.09 minus 0.05 would be 0.04. So we have 0.04 for this part. And then let's take a look at this part over here. This part. And this part represents B intersection C. And we know the probability of B intersection C is 0.13. So this part over here would be 0.13 minus 0.05, which is 0.08. So we have 0.08 for this part here. And then let's take a look at this part over here. So this part represents the probability of A minus this part, this part, this part. Okay? So that would be 0.14 minus this part, 0.04. I mean 0.04. 0.04 minus 0.05 minus 0.03. So that would be 0.02 to get 0.02. Let me rewrite it clear. Oops. .02. And then what about this part here? This part over here, that would be equal to the probability of B minus the 0.03, 0.05, and 0.08 over here. So that would be a probability of B 0.23 minus 0.03 minus 0.05 minus 0.08. So that would be 0.07. So this part is 0.07. And then let's take a look at this part over here. This part would be equal to the probability of C minus the 0.04 minus 0.05 minus 0.08. So that would be the probability of C is 0.37 minus 0.04 minus 0.05 minus 0.08. So that would be 0.2. So this part here would be 0.2. 0.2. Now we have the probability of each part. We can find out the probability that is asked over here. Let me clean this here. Okay, so this is equal to A intersection B union C. So B union C would be, this part would be B union C. This part would be B union C. And A intersection B union C, that would be 0.03 plus 0.05 plus 0.04. So we have 0.04 plus 0.05 plus 0.03, that is equal divided by, of course, 0.23, and probability of B plus probability of C 0.37 minus the probability of B intersection C 0.13. And then we have this is equal to 0.12 divided by 0.47, which is approximately 0.255. So basically the key point of this question is to draw this Venn diagram. Once we have this graph over here, everything would be much easier. All right, let's take a look at part 3. So part 3 is asking what is the probability that A given read at least 1. So read at least 1. So read at least 1 means that it could be 1 out of those 3, it could be 2 out of those 3, and it could be all the 3. So the read at least 1 over here represents A union B and then union C. A union B union C. Now how can we find the probability of A union B union C? So based on what we learned in the previous video, we have the probability of A union B union C that is equal to the probability of A plus the probability of B plus the probability of C minus probability of A intersection B minus the probability of B intersection C minus the probability of A intersection C, and then minus the probability of plus the probability of A intersection B intersection C. And we can find each probability in this expression from the table here, and we just plug them in. We will have the probability of A in union B union C is 0.49. So the probability of A union B union C is 0.49, which means the probability that read at least 1 is 0.49. And then this would be equal to this is equal to the probability. So this is the probability of A given A union B union C. So this is equal to the probability that A intersection, so over here we'll have A intersection A union B union C. So of course the A intersection A union B union C, that would be just A. So we have the probability of A on the top here. Clean this, and then divided by the bottom, the probability of A union B union C. So what is the probability of A again? 0.14, which is given. And what's the probability of A union B union C, which is 0.49. 0.49. So if you type this in your calculator, you will have this is approximately 0.286. And then I have one more question over here. So once we have the probability of A union B union C, or once we have the probability that read at least 1 is 0.49, what is the probability that no one was right? So what's the probability no one was right? So in this case, we're going to think of the complement. So the complement of no one was right is at least one of them was right. Okay, so this is equal to the probability of A union B union C complement. Okay, and of course this is the probability of based on rule of complement, this would be equal to 1 minus the probability of A union B union C, and which is 1 minus 0.49, which is 0.51. So that's how we find the probability no one was right. So actually, this is a very important idea, because sometimes when we are solving for some problems of probability, it is hard or it is complicated to figure it out directly. So in that case, we always think of the opposite of it. So in other words, we think of the complement of it. Once we find out the probability of the complement and subtract that from 1, we'll find the probability we're looking for. That's what we did over here. The probability of no one was right, no one was right is the complement of at least one of them was right. Okay, so that's pretty much the idea over here. Okay, once this is clear, let's take a look at the number 4 here. I'm gonna clean this part. Clean this part over here. Okay, in this scale, we're looking for the probability of A union B intersection C. So this is the probability of A union B and then intersection C. And then divided by the probability of C, right? The probability of C. That's coming from the definition of a conditional probability. And in this case, we consider this union A union B as a whole thing. So once we apply the formula, that would be the probability of A union B intersection C divided by the probability of C. So what is the probability of A union B intersection C? So the A union B intersection C, that would be this part over here. This part. So that would be 0.04 minus 0.05, 0.04 plus 0.05 plus 0.08. So that would be 0.04 plus 0.05 plus 0.08, and then divided by the bottom probability of C, which is given up here, 0.37. And then if you type this in your calculator, you will have this is approximately equal to 0.459. So once again, basically the key point of this problem is to draw this Venn diagram over here. Once we know the diagram, we can find out the probability of each little part, and then we just basically, and if you know the formula, afterwards it's just a plug and play. So 2 key points of this question. Number 1, you gotta know the formula of the conditional probability. Number 2, you should know how to draw the Venn diagram over here. Okay, now, so once this is clear, let's take a look at the multiplication rule. The probability of A intersection B is equal to the probability of A given B times the probability of B. So actually this is derived from the definition of conditional probability. We know that the probability of A given B is equal to the probability of A intersection B divided by the probability of B, right? If we multiply the probability of B by both side equation, we have this will be cancelled out. The probability of A intersection B would be equal to the probability of A given B times the probability of B. And of course, we can do it the other way. So probability of B given A. So of course, in this case, the probability of B given A is equal to the probability of A intersection B divided by the probability of A, right? And then we multiply probability of A by both side equation. We're going to have the probability of A intersection B is equal to the probability of B given A multiplied by the probability of A. So why do we do this? This rule is important because it is often the case that the probability of A intersection B is desired, whereas both probability of B and A given B can be specified from the problem description. So consideration of probability of B given A gives the probability of A given B is equal to the probability of B given A times the probability of A. So of course, yeah, over here we can write down that this is equal to probability of B given A times the probability of A as well. Probability of A as well. They're completely equivalent. Okay, once it's clear, let's take a look at this example, 2.27. All right. The problem says we got 4 individuals have responded to a request by a blood bank for blood donations. None of them has donated before, so their blood types are unknown. Suppose only type O positive is designed, and only one of the 4 actually has this type. So if the potential donors are selected in random order for tapping, what is the probability that at least 3 individuals must be tapped to obtain the desired type? So what does it mean? What does it mean by saying the probability that at least 3 individuals must be tapped? So that means it could be 3 of them tapped or all of them tapped. Okay, so in other words, that means the first 2 don't have the O positive. Okay, so what we're doing here, first of all, we say we use B to denote first tap not O positive. Then what is the probability of B here? We get 4 people in total, and how many of them don't have the O positive? 3 of them don't have the O positive, and we have 4 in total, so the probability of B happens. The probability of B is 3 over 4, right? And then we use A is equal to the second tap not O positive. So the probability of A given B is, what is the probability of A given B? So given B means we have already known that the first type is not O positive, right? So after the first one, how many people left? We get 3 left in total, right? How many of them don't have the O positive? 2 of them don't have the O positive. Right? Because the first one is not O positive. We get, after the first type, we get 3 people left in total, and 2 of them don't have the O positive. So in this case, the probability of A given B is equal to 2/3. And then once we have that, the probability at least 3 individuals are tapped. So the probability at least 3 individuals are tapped is the probability of A intersection B. Why is A intersection B? So A intersection B means either the first one or the second one is not O positive. If the first 2 don't have the O positive, then the last 2, the third or the fourth, there must be one of them have the O positive, right? So I don't care if the third one have the O positive or the fourth one have the O positive. I don't care. I just need to know that if the first 2 don't have the O positive, then the O positive must be in the last 2. the last two individuals. So what we're looking for here is the probability of A intersection B. Of course, based on formula we just went over, the probability of A intersection B is probability of A given B times the probability of B. So the probability of A given B is 2 over 3 times the probability of B 3 over 4, which is, this is equal, I don't know why. Sorry. Get back. Here we are. Clear this. So this is equal to 2 over 4, which is 0.5. Okay. Now once this is clear, let's take a look at this part. What is the probability that all 4 individuals must be tapped? So if all 4 individuals must be tapped, then it must be that the last individual tapped has the O positive, which means the first 3 don't have the O positive. Okay? So we're looking for the probability that the first 3 don't have O positive. If we know that the first 3 don't have the O positive, then the fourth one must have the O positive blood tap. Okay? Now what we're doing here first is I will use C is equal to, the C is equal to the third type, not O positive. Then what is the probability that C given A intersection B? What does it mean? C given A intersection B. That means if we have known the first 2 people don't have the O positive type blood, what is the probability that the third one does not have the O positive? Okay, so after the first 2 tap, and we know neither of them has O positive, how many people left in total? We have 2 people left. And how many of them don't have the O positive? Only 1 of them don't have the O positive. So the probability of C given A intersection B would be 1 over 2. The reason why it's 1 over 2 over here is because we have already known that the first 2 people, A and B, don't have the O positive. After that, there are only 2 people left, and only 1 of them doesn't have the O positive. So the probability of 1 over 2. And then the probability that all 4 are tapped. So it's equal to the probability of A intersection B intersection C. Okay? We're looking for the probability that none of A, B, C have O positive. So, of course, this is equal to the probability of C intersection B intersection A. Same thing. So this would be equal to the probability of C given A intersection B times the probability of A intersection B. That's coming from the formula, right? So over here, we just consider this A intersection B as a whole thing. We consider this intersection as a whole thing. So what is the probability of C given A intersection B, which is 1/2? And what is the probability of A intersection B? It's 1/2 as well. So we have 1/2 here. 1/2 times 1/2, which is the 1/4, which is equal to 0.25. That's how we find the probability of this case. I wish it makes sense. All right, the last part of this the last part of the conditional probability is called Bayes' theorem. Actually, this is not the most important part in this class, but if any of you have a chance to take it a more advanced probability classes, and you will see this name a lot. So we wouldn't talk too much about this theorem. We just take a look at it for quick, and and take a short proof. Now let's take a look at this. So let A1 through AK be mutually exclusive and exhaustive events. So exhaustive means that those events are consist of partition of the sample space. Then for any other event B, the probability of B is equal to the probability of B given A1 times the probability of A1 plus through probability of B given AK times AK. If we wanna put it in a form of a summation, it's gonna be from I is equal to 1 to K, and the probability of B given AK times the probability of AI. So let's take a look at Y. So for example, let's say let's say I is equal to 4. Of course, I could be any number greater than 1, so I would just, let's just prove it when I is equal to 4, okay? What I would do first, I would draw a picture. So this is sample space, and let's say it's 1, 2, so we have A1, A2, A3, and A4. Those A1, A2, A3 are exhaustive because there's a partition, right? Okay? And I will draw B over here. This is B. This is B. Then I will say that B would be equal to the union of this part. So this part here is going to be the intersection of B and A4. And this part over here, which is the intersection of B and A2, and this part would be the intersection of B and A1, and this part in the middle, so that would be the intersection of B and A3. So in other words, B is equal to the union of B intersection A1 union B intersection A2 union B intersection A3, and then union B intersection A4. So the whole B here is the union of those 4 shaded area. And then we're going to have the probability of B is equal to the probability of this whole thing. And we know that all those 4 parts are mutually exclusive. Then we're going to have the probability of B is going to be equal to the probability of B given B intersection A1 plus the probability of B intersection A2 plus the probability of B intersection A3 plus the probability of B intersection A4. Now, based on the multiplication rule, we have that the probability of B intersection A1 is the probability of B intersection A1. No, B given A1, I mean. B given A1 times the probability of A1. And then plus the probability of B given A2 times the probability of A2. And then plus the probability of B given A3 times the probability of A3. And then plus the probability of B given A4 times the probability of A4. Of course, if we want to put this in a form of summation, that would be the sum of, let's say, I is equal to 1 from 1 to 4, and then probability of B given AI times the probability of AI. So which is the form of given here. That's how we got the Bayes theorem, okay? So I wouldn't talk too much more about this. And I just wish that once you say something about Bayes theorem in the future, you'll say, okay, I see something like this before, and that's it. All right, that's pretty much all about this part, conditional probability.